So by definition, if we know this, in a graph or hypergraph, if we know that the number of edges of G is bigger than the extremal number, that means there is at least one copy of F inside of G. So you can ask that if there are, the number of edges a bit more bigger than the exponent number, then can you find the many copies of F? So in fact, we can prove the following theorem, which is called supersaturation. So for any R uniform hypergraph F and say small epsilon, there exists delta and n0 satisfying the following for all n at least n0. If G is an n-vertex R graph G with number of edges more than the, say, Turan density plus epsilon times nr. So remember that the Turan density is roughly, extremal number of F divided by n choose R. And of course we let n to go to infinity, but that was the Turan density. And this is essentially the threshold. So this times this is essentially the extremal number, but you add small number epsilon times n choose R. Then this is a bit over the extremal number, then suddenly G contains many copies of F, at least delta times n choose F copies of F. Let's say on F vertices. So let's say this F, the R graph F is on F vertices, small f. So first we choose K be a large number. So basic strategy is as follows. So we have G, which has a bit more than extremal number of edges. So there are many edges here. Then what we show is that there are many sets of size K, where K is some number much larger than F. So there are many sets of size K, which has also kind of many edges inside. We can show this because G has many edges. Once you take a random set of size K, then we know how, in expectation, how many edges are there, and we can show that many sets of size K actually have many edges. And because on this set of size K, we have many edges, so we can find a copy of F in each K set. And there are many K sets, so we get many copies of F. And then some of them are the same copy, but we have to deal with them later. So we choose this K first. So we choose K large enough so that extremal number of F regarding to K is smaller than pi of F times plus epsilon over 2 times n choose R. K choose R. So by the definition of this Turan density, this is limit of extremal number of nf over n choose R. This is pi f. That means if we choose large enough number, then this ratio is smaller than this density plus arbitrarily epsilon 0 that we want. So we take epsilon 0 as epsilon over 2. Then we can find such k. And we claim that there are at least half times epsilon times n choose r and choose k sets k of size k such that if you take the G induced subgraph of G induced by the set K has more than pi f plus epsilon over 2 times K choose R edges. Because this is true, because otherwise what we have, if you choose all sets of size K and we consider the number of edges in each hypergraph induced by the set K, then what do we have? We have n choose k many sets, which has at most n choose k many sets, which has less than or equal to this many edges. And we have, by our assumption, assume this is not true, there are at most half epsilon times n choose r many 1, which contains, at most k choose r many edges. So we know that this is k vertex r graph, which has, this is maximum possible. So again, we assume that there are at most this many sets k such that this has more than this many edges. So those are contributing at most this much to here. And then rest of them, the number is less than this. And all of them has smaller than equal to smaller than this many edges. So we have this inequality. But what's this? If you just compute it, we get this. But in this expression, on the other hand, in this expression, what do we count? If we have an edge of size r, then whenever we choose a k containing this, then this edge is counted. But how many times of, how many sets of size k containing specific r vertices is n minus r choose k minus r many. You just choose remaining k minus r edges. And each edge is counted this many times, and there are the number of edges in G many edges. And because we assume that the number of edges is strictly bigger than this number, this is m minus r choose k minus r times pi of f plus epsilon times n choose r, which is pi of f plus epsilon times n choose r times k choose r. But this number and this number are same. One, we said that this is strict lower bound. One, we said that it's upper bound. also a contradiction. So this claim is true. Then, by the choice of K, each of these K sets, this set of size K, which contains more than this many edges, contains a copy of F. So the number of copies of F is at least epsilon times n choose R over 2 divided by n minus F choose K minus F. We have on the bottom because to deal with the multiple counting. So here we count this F for specific set K. But how many sets of size K are there which contains this specific copy of F? You have to choose K minus F more vertices. Then we find the set which contains the copy of F. So each copy of F can be counted at most this many times. And again, sorry, this is actually K. And this is half times epsilon times K choose F to the negative 1 times n choose F. Hence, by taking delta as a half times epsilon times K choose F to the negative 1, we prove the conclusion. So this shows that for given epsilon, there exists delta, so that if n is large enough, any R graph with strictly quite more, epsilon times n choose R more edges than the extremal number, contains roughly some constant times n to the f many copies of f. So you can find many copies of f here, so which is called the supersaturation result. So by using this and the following concept, we can actually prove the Ehrlich-Stone-Simonovich theorem, which we have proved in the undergraduate graph theory with a different method. For that, let's define a concept. For a graph F and say V in this vertex, this graph F, we consider new vertices V1 to Vt. So for each vertex of F, we consider new vertices, T new vertices. Then we write F of T be the T blow up of F, which consists of vertices Vi for all vertices in F and I between 1 and T, and H's Ui and Vi, Vj, Uv is in H in F, I and J in T. So for example, if we have this graph F, then F3 is each time you put 3 vertices instead of 1, and then you put the complete bipartite graph. between them. So this and this is complete, this and this is complete. So each edge is replaced with a complete bipartite graph. So this is complete, complete, complete. So by using the supersaturation result and the Ehrlich theorem, we can prove this theorem by Ehrlich and Stone-Simonovich, which says that for a graph F, we have the extremal number of the graph F is always 1 minus 1 over the chromatic number minus 1 plus little of 1 times n choose 2. So lower bound is easy. You consider the t sub chromatic number minus 1 n. So this is, let's say this is R, then R minus 1 partite complete graph. So any subgraph of this is R chromatic, R minus 1 chromatic. I mean, has a chromatic number at most R minus 1. So F doesn't, embed it here. So we cannot find F inside of this graph. So which immediately, provides a lower bound of this times this. So we only have to prove upper bound. So for that, let's prove one claim. For a natural number t, we have the two-run density of complete graph is same as two-run density of complete R partite graph with each part has size t, so which is t blob of this graph. So let's prove this first, and then we explain why this implies the Ehrlich-Stone-Simonovich theorem. So let epsilon be arbitrary small positive number. Then by supersaturation, there is delta such that any graph G with more than pi times k, pi of kr plus epsilon times n choose 2 edges contains at least delta times n choose r copies of f, kr. So we consider an auxiliary R uniform hypergraph, say Ox, on the vertex set VG, and its edges, its hyper edges, correspond to copies of f, meaning that we have a graph. If we have a copy of f, then we put a hyper edge on here. And if we have another copy of f, then we put another hyper edge here. That defines, even if there are more edges, it's still fine when f is here. That defines this auxiliary hypergraph. Then, by the previous theorem of Ehrlich, we know that the extremal number of R uniform, R partite hypergraph where each part has size t. So you put t vertices here, t vertices here, t vertices here. There are R sets. You add all the sets of size R, which contains one vertex here, one vertex here, one vertex here, one vertex here. Then that's this graph. Yeah. I think that we have used a different notation before. So we have used, so this is same as K sub T, T, R. Yeah. Let's write it this way. K sub, K super R, T, T. So, hence, so this is, strictly a little of n to the R. And what do we get? We have at least this many copies of KR in here. So this ox has number of edges in this auxiliary hypergraph is at least delta times and choose R. So if n is big enough, then F contains a copy of K super R sub TTT. So complete R partite R uniform graph with a color class size T. But so we have again, so this is not copy of F, sorry, copy of K sub R. Then what does this mean? We have a, let's say R is 3. We have a T vertices, T vertices, T vertices. And if you choose any 3 vertices, then they form a copy of K3. So if you find one vertex, one vertex, one vertex, then they form an edge in this auxiliary graph, meaning that it forms a copy of K3. That's true for all of them. That means that this, as a graph, this is a complete 3 uniform complete 3 partite graph. And this copy corresponds to a copy of K sub RT in G. And this shows the equality. So we get this. Because this graph contains this as a subgraph, so this direction is easy. But what we just show is that so this direction is easy, but what we just show is this direction also holds with adding epsilon for arbitrary epsilon. So this part is bigger than this. So, when you take the limit, that means they are the same. So now for R as a chromatic number of F and T be the number of vertices in F, then we know that F is a subgraph of K R T blob. So Turan's theorem implies that pi of KR is 1 minus 1 over R minus 1. Hence, the claim shows pi of F is also 1 minus 1 over R minus 1, which means this. So this proves the Eddington-Simonovich theorem. So this is another way of proving this. So what it means is that the Turan density of graph are always of this form. So for graphs have Turan density, all of them are from 1 minus 1 over R, and R is in natural number. So for hypergraph, it's a bit different. For graph, even, one thing is that we can even consider the extremal number of family, where is a family of graph. So that this is maximum number of edges in a graph G. Maximum number of edges in a graph G, where the G has n vertices, and G doesn't contain each f for every graph in this family. Then with this formulation, again, we can consider the Turan density of a family of sets. Then for graph case, again, you can show that this is all Turan density. So this is essentially the minimum of 1 minus 1 over extremal number of this, where each graph, for each graph you compute the chromatic number and you take the minimum and times n choose 2 plus liter of n square. So this is also known. And for hypergraph, you might also think that, okay, for hypergraph, we can also consider this Turan density, then does it have a specific form? But it is actually not true. Pickle in 2014 showed that there exists a finite collection F of hypergraph, uniform hypergraph, for R LD3 such that the extremal number of n to this, you consider this number is actually irrational. Okay, so we move to the next topic.